now we're going to listen to Arowolo Aminat, who is going to be presenting multimodal AI for agriculture, for forecasting agricultural risk or sports using satellite, climate, and conflict data. Arowolo Aminat, if you're on the call, if you can please unmute yourself and put on the video, and then the floor is yours. Thank you.
Yeah, good afternoon, everyone. Can you hear me, please? Please confirm if you can hear me.
Yes, we can hear you loud and clear.
Yeah, so I would like to turn off. My network has been quite unstable. If you notice, I've been going on and off. It has been very much frustrating. So in order for you to hear me clearly, I would like to turn off the video and then share my screen so that you could see my presentation slides.
Yes, your screen is visible.
Okay. Thank you very much. So my name is Aminat Arowolo. I'm a graduate from the Federal University of Technology, Accra in Nigeria, where I studied food science and technology. So I'm here to present the multimodal AI system for agricultural risk forecasting. So in recent years, food security has become more than just a farming issue. It is now shaped by many interconnected factors, which includes changing climate, political instability, and unpredictable weather patterns. So in order to tackle this challenge from a combined effect aspect, this study was developed by using a multimodal AI system that can combine different data sets to predict areas likely to face agricultural distress, focusing on sub-Saharan Africa, including Nigeria. So you can think of it as an early warning system powered by AI for humanitarian aid. So the major factor which drives the agricultural risk is the climate. It includes the climate-induced vegetation stress, the geopolitical instability, and the weather volatility. So the climate-induced vegetation stress, we talk about droughts, desertification, and irregular rainfall, which affects crops and vegetation health. Then talking about the geopolitical instability, we look into the conflicts and wars, which destroys farms and block food supply chains. This also displaces people. And looking into the weather volatility, we talk about sudden changes in the temperature or rainfall, making farming unpredictable. Take, for instance, if there is drought in a particular area, and let's say the northern Nigeria, for example, combined with local conflict. For instance, the farmers would not be able to grow or transport food, and that's how this combined effect actually deepens food crisis. So talking about the impact of these agricultural risk hotspots on food security. Hotspots are actually areas where multiple risk factors overlaps. When the climate shocks and conflict hit the same region, food security tends to collapse faster. It's like a chain reaction, right? Where one problem follows another. So the objective or the goal of this study is to find these hotspot areas earlier so that aid organizations can act before famine starts to occur. In order to the need for these humanitarian policies helps in early warning system. Yeah, it helps to enhance early warning systems that are necessary to predict and mitigate insecurity. It also helps in integrated data approach by combining data from climate variables and conflict events. We can provide a more comprehensive understanding on food security risks. To In order to make early predictions, we need systems that don't just rely on one type of data. We need early predictions that integrate data sets from these three streams, which include the satellite data, the climate data, and the conflict event, which is how we came about the multimodal AI framework, because this integrated diverse data source to predict or forecast agricultural hotspots in 1 to 2 months lead time. So moving to the next slide, where I explained the multimodal AI framework already, which integrates diverse data source to predict agricultural hotspots in 1 to 2 months lead time. I hope you can all hear me. My network has been very much unstable, but I hope you can all hear me clearly. Talking about the multimodal AI framework, integrates diverse data source to predict or forecast agricultural hotspots using the satellite data, the climate data, and the conflict data. The methodology used in this study involved 5 processes. It involves the data collection, the data processing, the models training, the model selection, and the model evaluation. The data collection is done to choose high data representatives. We talking about, like I've mentioned earlier, talking about the satellite data from the FAPA anomaly raster, the climate data from CHIPS and ERAS-5, and the conflict data. The data were carefully selected and cleaned, after which the data was processed to ensure that they are in the right format for our model. Then the model training was done to ensure that the data suits our objective and the architecture of the model. Then the model selection involved us selecting the ones that fits well into the architecture of the model that worked well for our objective. Then we have the model evaluation. For the data collection and processing, we had 3 streams of data, which I have mentioned earlier: the satellite-derived FAPA raster, the climate variable, and conflict event, which forms, the first stream of data, which is the satellite data, involved 3 processes, which is the RGB fusion, the grayscale conversion, and the resizing. So to explain this, the 3 rasters, which is satellite data, forms an RGB fusion. The RGB fusion means that it was aggregated by finding its mean to form a one-channel image, which is then converted to the grayscale, after which it was resized. We tried using the 256 by 256, but that did not fit well with our model. Then we resized it to 64 by 64, which actually performed well to fit into the architecture of the model we wanted to train it with. And for the tabular data, which is the climate variables and the conflict event, it's we processed it using 3 processes, which is the merging, the interpolation, and the normalization. For the tabular data, it was merged into one data set using the ISO 3Com, and after which it was normalized using the Z-score. This was done to scale and normalize this value to normal distribution. Okay, so moving next to the data training, series of experiments were performed to train the data to suit our objective. So we tested classical models like random forest and deep learning analysis, which did not, well, it was suboptimal because it could not use it. We could not use it with our neutral networks. So we also experimented using normal image classification method that didn't perform well also. All these challenges we faced prompted us to use a direct forecasting, which is 2D CNN. This basically works by splitting the tasks into smaller tasks. By building ANN, we built ANN, which classify the image and tabular data, which later fuses them together using the MLP for combining, and which later gave us a good prediction. So we found out that using the UNet for image-like data, like the maps or raster images, like satellite data, and LSTM. LSTM was used for time-based data, like the climate or conflict records. It gave us the best results for which suit our objective. Then finally, we fused everything together using an MLP model to make one strong prediction. To simply put this, the AI looks at the satellite images, it checks the climate trends and see if there are conflicts, and then predicts which areas are most at risk in the next 1 or 2 months. Our study majorly focused on sub-Saharan African, including Nigeria. Okay, so this is the final pipeline of the integration of the model that was used. I mentioned earlier that we made use of the units for the raster forecast. We used the LSTM for the tabular forecast and MLP for fusion. That is how our multimodal AI prediction worked, to using 5 months prior to forecast 2-month future as the best we could come up with. This is just showing the graphical representation of the model use, the model architecture, whereby I mentioned that we utilize the unit with the ResNet 50 to forecast the raster and the tabular data which helps in reducing performance bottleneck of one of the hotspot forecasts. Moving on to the results and the interpretation of the study. Our work showed that by integrating environmental and conflict data using multimodal AI, we can forecast agricultural risk hotspots 1 to 2 months in advance. This gives policymakers and humanitarian agencies it gives them a chance to act earlier before the crisis worsens. And from the results of this multimodal AI system that we used showed that the multimodal AI framework gave a 91% F1 score, which is greater than the single modality and classical approaches. Like the single modality mentioned here is referring to a single modal AI framework, whereas our study utilized multimodal AI framework from using satellite data, the climate data, and conflict events. And also we noticed that the grayscale was much more efficient and effective than the colored scale. Looking at the graphical representation that was featured in the slide, you would see that the grayscale is much more efficient and effective. And likewise, as other studies had also mentioned, the conflict variable is the key driver for agricultural risk hotspots. From our results and comparing to results of past works, actually the past works use single modality, but our own that also combined multimodal framework also showed that conflict variable is the key driver for these hotspots. Likewise, the short-term forecast is also much more effective than the long-term forecast. Our study used a 2-month forecast, which showed least average loss. This means that rather than using 5 months, rather than using 3 months upwards to forecast, this features the 2 months forecast is the best we could come up with in the experiment as shown in the graph. And also hotspots are very, very much sensitive to regions of vegetative stress. In the future, we aim to scale the system to other regions and improve its real-time monitoring capabilities for global food security. The next slide is explaining the SHARP model that was integrated in the methodology of the work. The SHARP helps to identify most influential feature in predicting the agricultural risk. Like the result as already mentioned, that the conflict data was the major driver of the agricultural risk hotspot. This SHARP model was the one that helps us to identify the most influential feature. And by using the SHARP model, the prediction became more transparent, validating results based on clear explanations and not just based on assumptions. The SHARP also enabled pinpointing of the key drivers, like I have mentioned earlier in this slide. So the conclusion of this work is that the multimodal AI framework integrating satellite-derived vegetation stress and climate data can significantly enhance the short-time forecasting of the agricultural risk hotspot with accurate explainability. Thank you.